We talk about the types of radiometers, give you a little more examples on these and break them down to a different characteristic spectrally. We haven't talked too much about that. I did think it is important to go over some how radiometers are calibrated. There are some uncertainties there to be aware of and just keep in mind. So I'm going to cover that, some measurement techniques, a brief view, spin through some field sampling methods, and then I'll also talk about a unique system called the sun photometer, just to give you some exposure to more atmospheric measurement using radiometry. So, excuse me. What does the in situ light we want to measure look like? This is for clear water. I think we've seen this before. In the black line is the surface irradiance right above the surface of the water. The red line is the upwelled or water leaving radiance, the radiance that's coming out of the ocean. As a function of spectral wavelength. And as you can see here, there's some very high resolution spectrally. We can see a lot of the Fraunhofer lines that we've talked about, some of the other peak absorption lines as well. There's a lot of detail here, and this really emphasizes the power of looking at a very high spectral resolution in both radiance and irradiance. The most common radiometric instrument types usually get defined by spectral resolution, for better or worse. It's also scaling with cost as well. There are really kind of three classes of sensors, commercially available sensors you can get. Broadband sensors, we just talked about the PAR in the last lecture. That's an example of a broadband sensor. But there's other ones that can be into the UV, a very small section of the UV, UVA, photopic sensors, and other sort of broadband sensors are available. There's multi-channel. These are just combinations of discrete wavelength sensors, usually somewhere between 4 wavelengths and 19 individual bands, typically 10 to 20 nanometers in width. And then there's hyperspectral instruments, which are much more continuous measurements made every one, as we just saw, nanometer to 10 nanometer across the entire visible and near IR spectrum. So we just talked about, I'm not going to go over too much more here because we just talked about the PAR sensors in the last talk, other than to say there are some issues with it, particularly in those spheres. There is some, due to some scattering in it, that sphere also can get cloudy or dirty as well. There's also reabsorption of these photons onto the detector. This ends up causing some issues. They become really difficult to calibrate, essentially. So these are some views of some of the commercially available PAR sensors or scalar PAR versions, but you also see various different planar PAR versions that are available as well. Typically, this is one of the more common used on many CTD rosettes. And in other applications, such as on profiling float applications, you'll see more of the planar type measurements for PAR. Second class is the narrowband or the multi-wavelength channel instruments. As I said, these are usually a collection of very discrete band wavelengths, discrete bands of wavelengths, 4 to 19 channels. Usually the spectral channels are defined by filters, usually an interference filter somewhere around 10 to 20 nanometer bandwidth. This is the bottom plot showing various different spectral bands on a type of, I think this is an irradiance sensor here. Photodiodes usually used in these behind the filter, and just as periodically, while it's continually, the photodiode is continually exposed to light, it's just periodically sampling the photodiode with a to D converter. These are typically pretty stable and pretty reliable instruments, have been around for a long time. A lot of the vendors will allow you to pick and choose your sets of different wavelengths. Many of them try to match many of the existing ocean color satellites bands, such as VIIRS or MODIS. There are some out-of-band effects on these. They typically are not really big, but you do need to consider these depending on which spectral bands you use in choice and your sensor. So what is out of band? Here's another example of two different filter sets and their response function. This one's not as clean, but this one is a little bit of clean in terms of the interference filter pass through. Each of these, if you measured it across, you would see a slight out of band signature at a lower wavelength. So here's what many of the commercially available multi-channel sensors look like. This is two versions irradiance for irradiance. You'll see in these configurations, there's 4 different cosine collectors here that we've talked about, usually discretized for the channel that you want to measure at. Lower half shows a couple of different multispectral radiant sensors. And so you see a glass window in front of that. And then in this version, I think that's 7 different Gershon tubes to measure the discrete wavelength bands. This one is an instrument for biospherical, has 19 channels. Last category is the hyperspectral wavelength instruments. Like I said, these are more continuous spectrum instruments. And they usually go from 350 down to about 1,000 nanometers. They typically use very small or miniaturized spectrometers with grating and prism for the dispersive elements. Usually they're fiber optic coupled into these systems. And then you use, again, a collimating mirror, a grating, and then a focusing mirror to spread out the light and disperse the light out across the detector array. These instruments, as you can tell, using a spectrometer, they can be a very demanding instrument characterization. What I mean by that, and understanding the thermal effects, stray light effects, a lot of effects that get much more prevalent with hyperspectral type, prism type, and spectrometer type instrumentation. The great part about this is because you're measuring across the spectrum, you can then discretize your spectra to match those of the VIIRS or MODIS or any ocean color channel width and response function. You could derive that from your full spectrum data. So here's a couple of examples of an upwelled light, upwelled radiance spectrum just below the sea surface, about 10 centimeters below the sea surface, 2 different realizations of that. And this is an example of a coarser spectral resolution. I think this is a 10 nanometer, so resolution upwell or downwelling irradiance spectrum. Some examples of them, what they look like, irradiance and irradiance sensors, 2 different hyperspectral instruments from Seabird Scientific, and then a variety of those as well are available from Trios. And then some really high twitch examples that have much more like 0.4, 0.5 nanometer spacing between the spectral resolution is MOBI. It's one of the classical Cal-Val sites off of Lanai, Hawaii that's been used for many, many years. And this is the picture of the inside guts of the MOBI system, where there's two different spectrometers down here. And everything is fiber optically coupled through the whole system. One system I'm working on is HyperNav system, where you can see the two small radiance heads that are fiber optically coupled into this body, where there's two independent spectrometers. So now that we know what all these instruments look like, we need to figure out how to calibrate them as accurately as we can. So calibration is just the process of quantitatively defining the sensor system response to known and controlled signal inputs. For ocean color radiometers, this is usually accomplished using a reference standard or standards that provides a direct realization of the radiometric quantity in SI units. While most commercial vendors, all commercial vendors do their calibration, it's really important to understand, and there's a lot of studies that have been done on this, even in the very, very best calibrations labs, getting an absolute calibration is very difficult. And typically most labs, even the best labs, still have 2% uncertainty in their calibration coefficients in the calibration systems that they provide. There's a good starting point here, the NASA technical data series. I'm covering it up, but it was the ocean optics protocols for ocean colors validation, and there's an instrument specifications section that's worth paying attention to. Sorry. So the starting point for radiometric calibrations is the primary standard is what's called the cryogenic radiometer. This is really only done at many of the world-class meteorological institutes such as NIST and the National Physics Laboratory in England. Basically, why do we use a cryogenic radiometer? It is a method to use electrical substitution technique where the optical power incident on an absorbing cavity is then compared to the electrical power required to heat that cavity to the same temperature. So again, it's a way to accurately use another measurement, heat and heat temperature, to quantitate that with the actual radiant power. It's cryogenic basically because to get the lowest resolution or the highest resolution they can and the sensitivity they can, they need to force it to a very low temperature to be able to get down to the heat flux that they can measure accurately. So this is the basic calibration equation for a field radiometer. Whether it's radiance or irradiance on the left-hand side, what you end up with is an in-air or a calibration factor, a way to scale the instrument counts to radiance or irradiance. An immersion factor, we'll talk about an immersion factor in a few slides here. And then we do the difference between the actual digital counts when the radiometer is sensing the light field minus the digital counts when the total light field is occluded, either by using a shutter or capping it off. Basically, it's just giving you what's called a dark reading noise or a dark reading it's a sort of a lower end noise level. Typically, most calibration facilities use a standard light source. A common irradiance standard is the 1,000-watt, what's called an FEL type lamp, shown over here in the right-hand corner. They have tungsten coiled filaments and a bipostate base. This is highly recommended by NIST and NPL as one of the primary calibration standards. It's a very bright light, 1,000 watts. It does do a lot of heating, but it's also highly sensitive in the calibration process to any dust or fingers on things that get on this actual glass element of it. So you have to be very, very careful never to touch that. Otherwise, your calibrations are going to be way off really quickly. Typically, you can purchase these from many different vendors. Buy these FEL lamps. They already come calibrated against NIST standards, and you get a data sheet that describes the spectral radiance coming out of the FEL lamp, usually at one set distance, usually about 50 centimeter distance away from it. One thing to note about these lamps, however, and that's what this plot shows, it's the wavelength versus irradiance, and the blue line shows what the actual irradiance is coming out of the system. And if you can recall back from the earlier graph, this is pretty opposite to what we actually see in the in situ environment. We usually have much more blue light than we do red light. So it is a consideration too, because if you look at it, when you're trying to calibrate a sensor, a hyperspectral sensor in particular, you have to have a light regime that can be sensitive enough across the entire spectrum. And it's often difficult because we want to have more blue light than we want red light, because usually we lose a lot of red light quickly in the ocean due to the water absorption. So this is one of the factors that we talked about too, in terms of why it's hard to calibrate and there's so much uncertainty in the calibration process. Is as you get down lower and lower, and the less light flux you're getting out from the blue region, the more uncertainty you're going to have in that calibration coefficient. So what does the setup look like for irradiance? Essentially, you have one of those FEL lamps that you align very accurately with an alignment. This is a top-down view, sorry. With a alignment laser that shines through the center filament of that lamp and then projects onto your cosine collector in the center of the cosine collector. You try to baffle this enough so that you don't, you're minimizing stray light inside of the room. And basically you just want enough light to fill up the area on the radiometer face itself. Again, as we talked about, because irradiance decreases roughly 1 over the distance squared, you need to account for that too if you're doing your calibration at a different distance than what the manufacturer of the FEL usually normally calibrates it at 50 centimeters or 500 millimeters. So there's a factor here you need to account for to convert from the 500 millimeter calibration distance to whatever distance you use in the lab. This is just some examples of different calibration lab setups that I've seen through the ages here. So again, you usually have one side of the room where you've got your light source, then you've got a set of shields or baffles that are just, you're able to zoom down the light enough so that on the backside where your actual target sensor is calibration, you can just change the illumination area very accurately. So in radiance, it's a bit different from radiance and how we calibrate things differently. Still sort of based on the same idea. You've got an FEL lamp, you've got some shields, but instead this time of putting the radiance sensor here, we're going to measure the radiance coming off a reflectance plaque. This is a real high reflecting plaque here, shown here. I'll show you some more examples in a minute. But recall what I said before, we know that irradiance attenuates 1 over distance, but radiance is conserved if there's no absorption or scattering with distance. So this distance really between the plaque and the radiometer test, the test radiant sensor, doesn't matter as much, but it is good to try to keep it closer to the face of the plaque rather than very far distances. So in this case, the radiance, sensed radiance at this, at the surface face is the irradiance coming off the lamp times the reflectance parameter, the reflectance, spectral reflectance off that reflectance plaque, divided by pi times, again, that same conversion factor for radiance, the calibration distance, square of the calibration distance divided by the square of the distance that you actually use in the lab. The irradiance standards, the big thing with the irradiance standards, these plaque standards that we just talked about, these reflectance plaques, is that they're close as possible to Lambertian reflectance plaques, meaning the light is getting reflected equally in all directions off of this plaque. So there are no patterns that you can see in just the reflectance across this plaque. Yeah. Typically, they're still even most reflectance plaques have a little bit of patterns in these plaques. So it is good to every once in a while when you get a new plaque, rotate it around, turn it upside down, left, right, so you can see if the actual value coming off the reflectance equates to be the same value. Most of these reflectance plaques are made out of a material called Spectralon, which has a really high reflectance factor across most of the spectrum. There are some other versions that are there, but they tend to have less uniformity across the plaque. Another way you can do this is by using an integrating sphere as another reference standard, where basically you've got a big giant sphere that's coated all around on the inside with this same kind of spectralon reflectance material. You put the light into this reflectance sphere, and then you, on an exit port, you measure out the radiance coming out of that sphere. So the idea here is to make sure that the light is really uniform, again, coming off this reflectance plaque. In this case, it's a sphere, so we don't have to worry about any planar inhomogeneity in this more flat face plaque. So spheres are used commonly. However, you do need to do a little bit of a modification here, because obviously you need light to kind of go into the sensor, to the sphere, light to come out of the sphere. So there is a modifying factor here called M, where you're looking at the actual reflectance of the sphere, and then you have to modify it so that you take into account the portions of this 4 pi sphere are excluded from the actual radiance, because you're losing light there. You might be reflecting light there. Because of that sphere multiplier here, the sphere is very sensitive to changes in surface reflectance. If that sphere gets dirty or it ages, you can see that's going to have a multiplying effect on the actual true value of the irradiance coming out. And as I just mentioned, you have light surfaces like a radiant sensor, which has a glass window. There is some back reflection also coming out back and forth, and even some stray light that may get into the system, unless you have a very constrained setup. All right, I'm just going to summarize here like what I talked about before. There's been a host of different studies round robins, sending radiometers from Cal Lab to Cal Lab. There was just another series done by European Space Agency with a whole bunch of radiometric ocean color sensors. Typically, the best in class, like I said, you'll still end up with a 2% error at best in just or 2% uncertainty in your calibration process. It's very difficult to do. Clean atmosphere, making sure that the irradiance coming out of those lamps is constant and invariant. Lamps age, there's secondary effects on the plaque, as I talked about. So it's very difficult to get a good to get a low uncertainty calibration without having 2% error. That all said, it's these measurements have been very fruitful and very worthwhile. But when you're trying to match up things like and calibrate or vicarious calibrate a spaceborne sensor, you need to account for these errors as part of your entire uncertainty chain. Okay, so let's talk a little bit about some other sources of error or uncertainty in these measurements, radiometric measurements. I'm not going to go through all of them, but we did mention a little bit about some stray light effects on the measurement itself. That's an instrumental effect. How accurate can you actually get the center wavelengths of each of your multi-band or even in your spectral band? Thermal effects, temperature changes. Does the actual instrument response go up or down, or is it constant? Are there a polarization sensitivity in your system? Many optics can change the polarization state, so you need to be aware of that as well. There's two other things I'm going to talk about because it is really more apropos to using these instruments in the field. The immersion effect and the cosine diffuser effect. There's also aging. So there's a lot of sources of error here if you're really going to try to do highly accurate radiometric measurements. You need to account for, or at least work with the vendor to get a grasp on what these uncertainty effects are. So let's start with the immersion factor. The thing we just ran through is, you notice all the calibrations for all these instruments, radiance and irradiance, are done in air. However, in most cases, we want to measure in the water. So what changes between the air and the water? The index of refraction. So for radiance, what I showed you is it's just a Gershon tube, usually with a glass window in front of it. So as you calibrate in the air, you're going to have a different index of refraction change across that the glass to air interface as you would from a glass to water interface. So you need to account for this and know that my calibration applies only to air. And if I'm using it in the water, I need to use a coefficient called the immersion factor to account for the change in the index of refraction as we move to water. There's methods to do this. Just from a computational aspect, you can just calculate it based on the air index of refraction of the glass, the material of the glass, the index of refraction of water, and you can even spatially do that more and get more complex with other optical, to include other optical elements if you want. But typically this is not really measured by instrument makers or manufactured in this, but you can do it experimentally. Typically for radiant sensors, they may just do a simple calculation to try to estimate the immersion factors. For radiance, however, it's much more difficult because you've got typically in these irradiance cosine collectors, you have a piece of like spectralon or some other plastic material that is good at diffusing light through it and collecting from all different angles. It's very difficult to estimate what the actual index of refraction of this material, because you'll also have usually an air gap and maybe even another diffuser stack up. So the best way to do this is to go into a lab and have very complex lab setup where you're measuring the irradiance right above a water surface from a light source that's coming into this tank, and then try to measure it right below the water surface. Very difficult to do, but I'm mentioning this just to make sure when you get a sensor, the calibration sheet you should get should also give you an immersion factor for air, which will always be 1, and an immersion factor when you use it in water. Make sure you're applying the right one. The cosine response, we talked about this in the last lecture a little bit. Essentially, this is what you want. You want your ideal collector to give you a cosine response. If you took a direct beam of light and then rotated around plus or minus 90 degrees, you would hope that that would map out as a normalization of the direct. You would hope that would map out as a cosine response. Typically, one of the things that are looked at on how well the cosine response is you just look at this normalized cosine response from the measurement you made versus a true cosine response, or a true cosine factor. And then you look at the difference between those two. And typically what you see is it does pretty well. It's usually 1 to 2% maybe error across most, up to like 45 degrees plus or minus, but then starts to break down again because of these edge effects. You get really hard to try to get those really high angles from literally 60 to 90 degrees without a huge amount of air coming into the system. Typically, you may see 5 to 10% error in the cosine response above 60 to 90 degrees, but less than 1 to 2%, usually between 0 and 30 degrees. The other part of this is to remember, as I showed you all this, not all cosine collectors are created equal. So this is really the trick part of, in my view, working in the industry for a long time, of a good radiometric sensor. Creating a very good cosine collector is a challenge, particularly one that can withstand the ocean, be resilient, and also survive over hundreds of meters of water as a pressure. So pay attention to that. See when you're purchasing it, just check to see on the manufacturers what their cosine collection efficiency is, or effect is, or error. Also, many irradiance sensor manufacturers use different cosine collectors for air and in water. So that's really important, and that helps with, of course, you got to have a good cosine collector. But that cosine collector also has an immersion effect as well. And so most vendors have found that the same material they might use in the air for the cosine collector is not the same material they would use in the water for the cosine collector, because they don't work equally as well in both conditions. So that's the forewarning. Do not use an irradiance sensor that is specifically designed to operate in air and use it in water. Otherwise, you will get a bigger error in your response, or vice versa. So just pay attention to that when you buy and look at these sensors. Is it designed to work in the air, this irradiance sensor, or is it designed to work in the water? Radiance is not as impactful on that. You can use these typically, I forgot to say that, you can use radiance sensors in both air and water. The immersion factor doesn't really change as much. What will change is the solid angle between the two systems. Typically, radiant sensors you buy for the water have a bigger solid angle because you're trying to collect a little bit more light. In the air, they have a smaller solid angle. It's usually 3 degrees half angle. In the air, it's usually about 8 degrees in the water, half angle. Okay, now let's move through how do we measure this, and what are some typical ways we measure and get at downwelling irradiance? We talked about this already before. The irradiance sensor essentially mounted above water somewhere. It's usually called your deck reference sensor, just to capture the amount of downwelling light as you're making a measurement in water, and to look at any temporal variations as clouds and sky conditions change and the illumination conditions change. Some things that affect the measurement uncertainty here are obviously the radiometer that's going to be there in every one of these figures. The tilt of the sensor. If the system's tilting a whole lot, you're no longer playing parallel. You're moving back and forth and looking at different fractions of reflectance off the water versus what's coming out of the sky and the sun. Shading. You never want to have the sensor be shaded by anything. A bigger superstructure of the deck. Those kinds of things. Otherwise, you're just measuring usually the sky condition of irradiance. Fouling, unstable illumination. Second method is used primarily, again, in the upwelled condition, or the upwelling, sorry, not the upwelling. It's typically used in the above water condition. Here is the reflectance plaque measurement, where you have a radiant sensor. You're collecting light coming off this plaque from the irradiance coming down from the sun and through the atmosphere. It's kind of similar to what we talked about before in terms of the in-lab calibration technique. Lots of things you need to account for here. What we talked about, the plant calibration, getting that done. Some by reflectance functions and how that pertains to the actual radiance being measured, and plaque homogeneity, tilt, fouling, shading. The last one, which I'll end this whole talk with, is another application called sun photometry. It's really good for atmospheric modeling inputs and deriving some constituents or some understanding of what's in the atmosphere. Put in a good reference here. Actually, this entire set of references inside of this one journal publication that came out has a lot of good information on how to do good in situ radiometry. So in terms of the upwelled water leaving radiance, there's 4 different methods here. I'm not going to go over each one of them. It's in the detail here. First one is more classical. Mount your sensors at various different depths in the ocean. This is what a system like Moby does, 3 or 4 depths where you have upwelled radiance sensors mounted at each stage. And that allows you to at least calculate the radiance at 3 or 4 points. And then as we get into on the IOP lecture, you can calculate the diffuse attenuation, the rate of change in the irradiance between those, and kind of fill in your vertical profile. There's an underwater profiling system. That's one of the more commonly used, where the radiometers are mounted on a profiling system that is dropping pretty vertically stable as much as you can at a rate. So you're just getting a full vertical profile of the radiance. There's an above water method that's commonly used too, where you've got 2 radiant sensors, one looking at the radiance coming out of the ocean, and another one looking at the radiance coming from either the sky or from the solar beam. And then there's a fourth method called the sky blocked, where you take a radiometer and you stick on a big cone on it, and you stick that cone just barely in the water. What you're doing there is you're blocking a lot of the skylight radiance coming in, and a lot of the sunlit potential for interfering with the upwelled radiance measurement. So you'll see a lot of these different setups, configurations in a lot of the literature. Just each one has its own set of measurement uncertainties here that you need to pay attention to and look at and see how they corrected for those. So again, here's some more examples. Just I like to always throw in some pictures. There's another irradiance sensor can be used on a free fall system stuck in here. So you're always getting the downwelling irradiance spectrum as this system falls through the water. These are some irradiance sensors mounted on another big optical buoy called Boussole. Here's a couple of pictures of that above water method I talked about, where you got the two different angles, measuring sky irradiance, and then rotating that head back around and measure the radiance that's coming out of the ocean. So this allows you to at least take into account what contribution of the sky irradiance, and if you do this right with your setup, you get rid of out of the glint pattern as well, and so you're able to really then take the water that you have from the downward pointing measurement and subtract off the skylight contribution to that. This is another way, instead of using a rotating head, just kind of flipping it back and forth between the two different sky and sea radiance measurements. You can also just measure them at the same time using two different instruments. The one advantage here in using this one system that's going back and forth is you're using the same irradiance sensor. So if there's a calibration error in this sensor, both measurements are going to have that calibration error when you do the difference. So that calibration error comes out. However, when you're using two different radiometers, and if they don't have the same calibration error, when you do the difference, you could have a bias, a residual bias, if you have a calibration error that's different between the two heads. What we mostly do most of the time for ocean color validation is really use a profiling system. We're usually typically measuring downwelling irradiance on one head and upwelled radiance on the other head. Or we do this a lot from moorings, as well as the one configuration I talked about is putting your deck reference sensor to measure the incoming downwelling irradiance just above the water surface. Now, we talked about some of the field methodologies, what there are, and some of the uncertainties. We just talked a little bit about those in the last figures. The self-shading, platform shading, making sure your sensor's never in the shade of a system or a measurement. The tilt effects, a lot of these profiling systems tilt, as well as mounting those heads on the decks. Those can affect the signal as well. There's another effect then talked about, wave focusing. I'm going to focus on that in the next few slides. As well as making sure you have very accurate depth, because again, once we talk a lot more about how K is derived, you really need to know accurately the depth between those two intervals to be able to extrapolate appropriately that radiance to the surface. There's also surface transmission, potential sources of error there, depending on a variety of different factors in terms of wave transmission. There's a lot of boundary effect errors you may need to actually consider. Put in this paper, or this protocol series from IOCCG, sort of the updated one to the original NASA manual that came out in the early 2000s. So this one's a really good updated version, and I encourage you all. It's available, I think, online from the IOCCG site. So what are wave focusing effects? Well, if you ever been on a clear sunny day on an outdoor pool, swimming and looking down when there's a lot of kids splashing around, you'll see all these little dancing light and dark patterns floating across the bottom of the pool. Well, that's because you can think of it when a wave comes across it, it's acting like a little bit of a lens. You got some curvature. It's not a plain parallel situation. It's just flat as can be. You've got these little lenses, convex, concave lenses that fill in the crests and troughs. And what those do is they bend the light. You end up getting these little focus hot areas where both sides of this crest are coming down and now hitting one focal point. And the reverse is in the trough. They're spreading out light, so you'll get a dark point here. That's why you see that pattern on the bottom of pools. Now, when you're doing a profile up and down and you're trying to profile with all these different wave facets and surfaces, and remember, waves come from capillary waves up to big giant surface gravity waves. So there's a lot of complexity in these fields, and that's what this figure is showing, is just the bright dark patterns based on these different wave surfaces with depth in the radiance pattern as you try to profile through this system. So as you profile through this system, you may look like you have something like this in terms of its profile. It looks really noisy, and you're thinking, what the heck? This looks like cruddy data. The sensor's not working. Well, in wavy conditions, this is very real. It's a wave focusing effect, and it makes it very difficult to actually try to extrapolate what the actual or measure what the actual radiance is at that level. If you did, we were able to simultaneously, this is all a model output, if you were able to simultaneously make 200 profiles in this wavy surface at one time, this is what you'd end up looking like on that sort of realization through the system. It is somewhat real, but how do you average this out to get a much more reasonable looking radiance field? So when you're looking at data, when you're profiling, and it's kind of wavy out, it's not a calm flats condition. You got a lot of different wave height structures, capillary to don't be surprised if you see your data look a little noisy. There's one way to do this repeatedly, a whole bunch of profiles fast as you can go, or go really, 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 really slow as your profile. Collect a lot more data so you get a better average. All right, the last section I last section I wanted to cover is called sun photometry, and it's a way to get at the atmospheric optical depth. No, I skipped one. Okay. So the way this sensor works is it is really a radiant sensor, but it looks more like a radiant sensor, but it has a very, very tiny field of view, basically, for the irradiance port. It's a very, very tiny field of view. You take that sensor, you point it directly at the sun just based on calculating where the sun is, azimuth and zenith angles, program it to this point. This is a handheld version. So if you're just looking mostly at the fill of the sun, you're looking at the atmospheric transmission, the path through the transmission, and then you're looking mostly at the solar beam, basically. So by use of Beer's law, the irradiance we're measuring should be the irradiance at the top of the atmosphere, what's called the extraterrestrial solar irradiance, which has been predicted, and there's various models out there that correct for the Earth-Sun distance, and it's routinely measured. Well, it's not routinely; it's measured occasionally to make sure that those tables are kept with lowest uncertainty. So you take that extraterrestrial radiance, top of the atmosphere, that's times by the exponential of the actual thickness, the optical thickness of what's called the aerosol component, but it actually does include molecular as well. But it's the thickness of the depth of the atmosphere. And you times this by a funky parameter, I'm not going to go over, it's a little screwy to explain, another parameter called air mass, which tends to be where some of these systems have an error in this parameter. But what you end up getting is if you know all these parameters, you can calculate that aerosol and solve for the aerosol optical depth. Many of these sun photometers have multiple channels on them, discrete channels on them. There's two different versions, really. You can, two different ways you can do this, handheld or on a deck. But you get out basically the aerosol optical depth as a function of wavelength from these instruments. Why is that important? That's going to come into important as we try to atmospherically correct this data, atmospherically correct the satellite data to remove the atmosphere contribution to what the satellite sees. These measurements have been made for many, 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 many years. And in fact, there's a global array of these ground-based remote sensing aerosol optical thickness sensors. It's a network called AeroNet. And so just search on AeroNet and you can see the hundreds of stations that are across the globe that are measuring these components. Speaking of the atmosphere, I had the chance to go up a year or two years ago, I guess now, with Robert Fruin and make some really interesting measurements using that plaque method with our HyperNav system. And we got to go to the top of Mauna Loa to do it. So it's a beautiful day, not today out there for radiometry, but hopefully tomorrow. Thank you. Questions?
Write down questions and then you can submit them. Okay, we're going to write down questions. Let them think about it a little bit, and then I'll submit them to you and you can answer them on